Well, right now is a great time to be a watchmaker. There's so many exciting things going on, and there's a huge demand. We don't have enough watchmakers, so we're hoping to plant the seed in the minds of people who like working with their hands and like creating things, that there is a real job out there that pays well, where you can work with your hands, make things, and work with tiny machines. I'm Jordan Ficklin. I'm Executive Director of the American Watchmakers Clockmakers Institute. I've been a watchmaker for about 10 years. I started at watchmaking when I was working in a jewelry store while I was going to college, getting a degree in computer science. And then I got really interested in watches, so instead of going into computers, I started working on tiny mechanical machines. You know, just being able to touch and actually manipulate things in the physical world was a lot more attractive than working on virtual things and programming. The mainstay in the watch world has been the same for the last 300 years. We still have lots of mechanical machines, spring-driven watches to work on. There is some new and exciting materials and technologies. More and more we're seeing companies working with 3D printing, with LIGA technology, with EDM, all kinds of neat technologies for materials. But in the service side and the assembly side of things, it's relatively the same as it's been for 300 years. I'd say the hardest part of working on watches is being able to focus on a little tiny space for the entire day. A lot of people say you must have to have a lot of patience. I wouldn't say it's necessarily patience, because I'm busy doing something all day long, but it's being able to focus on a small space and a small task for the entire day. This is a watchmaker's loop. You use it on one eye for looking at it. This one here is about a 10 power magnification. Most watchmakers work somewhere between about 4 power and 10 power on a regular basis. But when inspecting parts, they can go up to 25 or even 40 power magnification with a microscope or a stronger loop. So the focal distance on this is about right there. So that's how far away I am from things when I'm working on them. This is a watchmaker's lathe. Works like a woodworking lathe or a large machinist lathe. So I use a graver like this, high-speed steel, and you just put it up to the work and you start pulling off pieces of metal. So one of the things we're using 3D printing for today is especially for tool making. So these are movement holders. You can take the watch movement and put them in here while you work on them. These are battery tweezers. You need non-conductive tweezers when working on batteries. So we got some plastic tweezers here that were printed. With 3D printing, some people are printing watch cases and stuff today, but the tiny parts inside of watches we're not 3D printing yet. In the classical watchmaking training programs, you make a lot of the tools that you're going to use. This is actually part of a watch. This is bridges for a watch that were made on a lathe just like this one here. And these are some of the projects along the way. A winding stem for a watch. This is just practice filing squares. This is a little carrier for turning something, holding on to something very small in the lathe. Support tool. We work a lot in brass and steel. And when in school, you can see we start large, learning to file a square out of a round stock, and then getting progressively smaller till we get down to the actual scale of components in watches. Some of the basic tools that we use. It's the jeweler's saw, just for carving, cutting out the shapes of the metal. This is a wrench for opening the back of some watches. This is a diamond file for sharpening hardened steel objects. A graver, burnisher file, caliper for measuring very small items. This is a classical tool for removing the cannon pinion on a watch. This one's probably a good 80 or 90 years old. Watchmakers tend to have in their collection a combination of new tools and old tools, some of which aren't even made anymore, but are incredibly useful. So you hunt down some of those tools so that you can use them. So this to give you a scale of the kind of things we work on. This is a model of a balance staff in a watch. That's an axle which holds the balance wheel, which is the main timekeeping device in the watch. It will be fit on this axle. Here is a 100 times scale model. In the tray here we have some 10 times scale models, and then there's 100 of the actual staffs in that tray. So if you were to put those on top of a dime, they'd be about the size of the eye there on the dime. When teaching watchmaking today, we're lucky to be able to have the technology we do to blow up on a big screen using a microscope with a camera attached. In our world, we use mostly microscopes for quality control, for examining parts and looking for defects. Something like this goes, what, 40, 60 power, probably?
By the time you put it on the screen, you're getting 60 to 80 power.
60 to 80 power examining the components.
Depends on the size of the screen that you're using.
My name is Jason Champion, and I'm the program chair at Oklahoma State University Institute of Technology. And we teach watchmaking. We're one of the watchmaking schools that are here in the United States. We teach a holistic approach to watchmaking, including the customer service, parts acquisition, and cleaning of and polishing of the watch case. Well, these learning tools are what we used to use before we had the microscope and the televisions we were looking at a minute ago. This model is from approximately the 1950s, and this model is a huge magnification. It's about, well, the actual movement, production movement was about this large, so you're looking at about a ½ inch. This was blown up much larger so that we could take the same competencies that we can now show in a microscope and a camera. They had to be taught here in physical principles, so that as we look at things like the oscillator and the wheels and the escapement, we had to have models to be able to show what each of these components do, so that we could teach students how they need to be adjusted and how they need to be modified to be able to function properly. So this is a model of an escapement, which is a part that we can see inside the watch movement here, but this is actually what controls and distributes the power from the large mainspring back into the balance. So as the balance rotates around, that allows these parts to manipulate. This is a balance model. So with this model, we can actually teach moment of inertia, in shakes, what we're talking about when we have to center a hairspring, not only in the center but also in the flat. These are things that make a watch actually run more accurate or less accurate. This oscillator is what controls the actual timekeeping of a watch. So you've got the ability to increase or decrease the rate by moving these pins, and that's actually changing the practical length of this hairspring to make the watch either run slower or run faster. Many people are familiar with an alarm clock that has an F and an S on it. That's what this does. As you move it back and forth, it actually increases or decreases the rate of the watch by moving where these regulating pins are on this hairspring. So the shorter the hairspring, the faster the oscillator moves, which makes the watch run faster. If you lengthen that, it actually causes it to slow down.